What if some mathematical truth can never be proven? I'm Saba, and this is Hidden Math.
Consider the following sentence. This statement is false. Is that true? If so, that would make this statement false. But if it's false, then the statement is true. So the sentence flips its truth value every time we try to evaluate it. By referring to itself directly, this statement creates an unresolvable paradox. Notice what's happening here. The sentence is trying to evaluate itself. That's the dangerous ingredient, self-reference. The moment a statement points back at its own truth value, logic can become circular. And circular logic doesn't give you an answer. It gives you a loop. So if it's not true and it's not false, what is it? This question might seem like a silly thought experiment, just a playful trick of language. But in the early 20th century, it led Austrian logician Kurt Gödel to a discovery that would change mathematics forever. Not in poetry or philosophy, but inside mathematics itself. Gödel's discovery had to do with the limitations of mathematical proofs. A proof is a logical argument that demonstrates why a statement about numbers is true. For example, if we want to prove that the sum of two even numbers is even, we don't just check a few examples. We use definitions. An even number is something like 2k. Then two evens are 2a and 2b, and their sum is 2a, still divisible by 2. That's what a proof looks like. It explains why something must always be true, not just why it seems true sometimes. It is mathematics' highest standard of certainty. The building blocks of these arguments are called axioms, undeniable statements about the numbers involved. Axioms aren't obvious facts in the everyday sense. They're the rules of the game. A theorem is something you prove using the rules. An axiom is something you agree to accept so proofs can even begin. And once you choose your axioms, everything that follows depends on them. Every system built on mathematics, from the most complex proof to basic arithmetic, is constructed from axioms. They are the foundation under every equation we write. And if a statement about numbers is true, mathematicians should be able to confirm it with an axiomatic proof. Since ancient Greece, mathematicians used this system to prove or disprove mathematical claims with total certainty. That tradition created a powerful dream. Mathematics is the perfect machine for truth. Feed it a question, and, at least in principle, you should be able to grind out a proof or a disproof. No mysteries, no gray areas, just certainty. But when Godel entered the field, some newly uncovered logical paradoxes were threatening that certainty. They hinted that something might be deeply wrong with the foundations. Prominent mathematicians were eager to prove that mathematics had no contradictions. Gödel himself wasn't so sure, and he was even less confident that mathematics was the right tool to investigate this problem. While it's relatively easy to create a self-referential paradox with words, numbers don't typically talk about themselves. In ordinary math, statements talk about numbers, like 7 is prime, or there are infinitely many primes. They're about objects in math. They are not usually about the statements themselves, and that difference sounds tiny, but it's exactly the gap Gödel learned to cross. A mathematical statement is simply true or false. But Gödel had an idea. First, he translated mathematical statements and equations into code numbers so that a complex mathematical idea could be expressed in a single number. Think of it like giving every symbol, every equation, and even every proof a unique ID number, almost like a barcode. Once you do that, you can use arithmetic to manipulate those IDs. And suddenly, doing math on numbers becomes a way of doing math about mathematical statements. This technique is now called Gödel Numbering. This meant that mathematical statements written with those numbers were also expressing something about the encoded statements of mathematics. In other words, equations could secretly describe other equations. In this way, the coding allowed mathematics to talk about itself. Through this method, he was able to write, "This statement cannot be proved as an equation," creating the first self-referential mathematical statement, a sentence of mathematics that points directly at its own provability. However, unlike the ambiguous sentence that inspired him, mathematical statements must be true or false. So which is it? If it's false, that means the statement does have a proof. But if a mathematical statement has a proof, then it must be true. This contradiction means that Gödel's statement can't be false, and therefore it must be true that this statement cannot be proved. So we are forced into an astonishing conclusion. Yet this result is even more surprising, because it means we now have a true equation of mathematics that asserts it cannot be proved. This is the key twist. True is a claim about reality inside the mathematical world, but provable is a claim about what your specific rulebook can demonstrate. Gödel separated those two ideas, and once they separate, you can have truths that live outside the reach of your proofs. Truth has escaped the reach of proof. This revelation is at the heart of Gödel's Incompleteness Theorem, which introduces an entirely new class of mathematical statement. Statements that are true, but unreachable. In Gödel's paradigm, statements still are either true or false, but true statements can either be provable or unprovable within a given set of axioms. Furthermore, Gödel argues these unprovable true statements exist in every axiomatic system. This makes it impossible to create a perfectly complete system using mathematics, because there will always be true statements we cannot prove, no matter how powerful the system becomes. Even if you account for these unprovable statements by adding them as new axioms to an enlarged mathematical system, that very process introduces new, unprovably true statements. It's like trying to finish an endless book by adding pages. Each time you expand the system to capture one missing truth, the system becomes powerful enough to generate new questions it can't settle. The horizon moves forward, but it never disappears. New walls appear every time we extend the map. No matter how many axioms you add, there will always be unprovably true statements in your system. It's Gödel's all the way down. This revelation rocked the foundations of the field, crushing those who dreamed that every mathematical claim would one day be proven or disproven. While most mathematicians accepted this new reality, some fervently debated it. Others still tried to ignore the newly uncovered hole in the heart of their field. But as more classical problems were proven to be unprovably true, some began to worry their life's work would be impossible to complete, that the ultimate proof might not exist. Still, Gödel's theorem opened as many doors as it closed. Knowledge of unprovably true statements inspired key innovations in early computers. Because once you admit there are limits to proof, you naturally start asking, are there limits to computation too? If proofs are procedures, maybe some truths are beyond any procedure at all. That line of thinking helped shape theoretical computer science, especially questions about what algorithms can and cannot do. And today, some mathematicians dedicate their careers to identifying provably unprovable statements. So while mathematicians may have lost some certainty, thanks to Gödel, they can embrace the unknown at the heart of any quest for truth. Gödel didn't tell mathematicians to stop searching. He told them the search will never completely end. And that's not a tragedy. It's a kind of freedom. It means there will always be something deeper to discover, even in the most logical universe we've ever built.
Gödel showed us that mathematics isn't broken, just beautifully incomplete. If you enjoyed this video, subscribe for more stories about the hidden side of mathematics.